Hello again. In this video, I would like to present you a first look into 6 months of infrasound recording in Jöhlingen. And special attention will be given to a certain infrasound signature, so-called microbaroms. You can find a detailed explanation on the processes generating microbaroms on Wikipedia. In short words, microbaroms are far-traveling infrasound waves which are generated by rough seas. So we could say it's the voice of the sea. The generation mechanism is due to superposition of ocean waves traveling with different frequencies into different directions, and then this superposition generates wave groups. And if the conditions are as needed, then the resulting speed of the wave groups can be rather large, in the range of 300 meter per second, so equaling the atmospheric sound speed, and in this case atmospheric infrasound waves are generated. These pressure waves then can travel over very long distances, thousands of kilometers, and different modes of propagation are realized in the atmosphere, either in the lower troposphere or higher up in the atmosphere in the stratosphere, or even in the lower thermosphere. The frequency range of these natural phenomena are in the order of 0.1 to 0.5 Hertz, with amplitudes in the range of microbars. In the previous videos, I outlined the technical setup of the homemade infrasound sensor, which you see here on the left image. It basically uses a subwoofer as detecting element and is a rather cheap device, but it offers excellent sensitivity in the range under consideration, the infrasound range, in the 0.02 to 100 Hertz range. So infrasound would be 0.02 to, let's say, 20 Hertz. I typically look at the signals in the 0.02 to 34 Hertz range. In order for calibrating the subwoofer sensor, I also built this kind of sensors. I did not mention it in the video. So this sensor is based on differential pressure sensors, which are measuring at a reasonably fast rate pressure differences between the outside and this reference volume. Typically, if used for measurements, I wrap the reference volume into a thermal insulation. Otherwise, temperature changes of the reference volume are misinterpreted as natural outside pressure differences occurring. It's also a cheap device in the same price range. It has the advantage that it is calibrated in absolute units. It is more sensitive at very low frequencies, but less sensitive at higher frequencies. So I would say about a few hertz, 1 hertz, this unit here is significantly more sensitive. Where I am located, the sensor I'm discussing in the following is located in Jöhlingen, which is a small village east of Karlsruhe. So we are roughly in the center of Europe here, and you see that the North Atlantic and the North Sea area are not so far away. and often we have heavy storms here outside in the Atlantic. A closer look reveals that actually I'm operating by support of friends hosting these kind of sensors, several sensors in the region of Karlsruhe, so it's already a little array. This is the Jöhlingen sensor, this is a sensor south from Karlsruhe, nearby Ettlingen, and this is a sensor north from Karlsruhe, near the village Leopoldshafen. And you see these are 5 kilometers, at the distances between the three sensors are in the order of 15 kilometers. My hope is that with accurate GPS referencing of the time scale, I can triangulate to pin down technical sources in the area. It's harder than I assumed to do this, but this is ongoing work. Perhaps I have to move the three sensors closer together to improve the measurements. The technical sources, I often observe them only in one or in a pair of sensors and not as the idea is in all three sensors. So now let's have a look into the spectral signature of these microbaroms. Note that these are the Audacity quick looks as I used them before. So here on the frequency and on the time scale, a scaling factor of 1/176.4 applies. These are not original, but these are higher than original frequencies. You have to divide them by 176. And you see in this 12-hourly record a band of increased noise level, and this are the microbaroms we are looking for. Now, calculating real frequencies, you see that the maximum is in the range of 0.2 Hertz, and it is not an artificial signal due to some resonance effect in the subwoofer or so. I can do exactly the same observation using the reference sensor, which is using a very different principle of detection. Let's compare this observation with literature. For example, these authors made a paper where they used normal, near normal, very accurate barometers, which have a sufficiently high repetition cycle in data recording, and they also calculated the microbarom signatures from their reading. You see that their observation has a bit lower spectral resolution than the sensor I used, but overall it's very similar. This steeper and shallower rise and fall as function of frequency with a maximum around 0.2 Hertz. So this is the spectral signature of the microbarom. And now if you are taking observations over an extended period of time, you are able to see the variability of the phenomenon. Depending on the state of the sea and depending on the state of the atmosphere, which either better or not so good supports the distribution of the signal. This is a day in early February where the signature is very, very strong, very pronounced. So this peak here in the frequency analysis of Audacity, so here again wrong frequencies. Here it is located around 40 Hertz or so. this maximum. And a couple of months later, in summertime, mid of June, it is a much calmer signal. You can still detect it, but it's much less pronounced. Also, the background changed a lot between the rough weather and sea conditions in February and later in June. On the other hand, you can see very clear near monochromatic features in this signal here, these stripes, which are, I shortly mentioned it in the first video, which are signals from wind farms. So these are technical man-made signatures. And this is a look at the whole time series, so the first half of it. These are data from January to early April, so roughly 3 months. I merged all the 12-hour files together into one big file. And yeah, you nicely see the microbarom feature, sometimes calmer seas, which has a tendency to get weaker and weaker in spring because the sea has a tendency of becoming calmer in summer. But there are other interesting features as well, as this band here around 8 and 11 hertz. The lower band sometimes shows a complicated double structure. These two bands were at the very beginning of my interest into infrasound. At that time, I used a very simple Android app to record spectrograms, and I used a little external microphone on the smartphone. I was lucky that this type of smartphone obviously supported low enough frequencies to be observable. So I was able to see these 8 and 11 hertz signatures already in these very early measurements. But I guess this is not a global phenomenon. This has something to do with the fact that I live in a hilly area near to the Rhine Valley. I think it's some kind of local music which I observe here. Okay, now let's have a look into the next 3 months, April, May, and June. You see that the microbarom is now becoming weaker and weaker. You can hardly detect it in summertime generally. The 8 and 11 hertz bands are still with us, but especially this 8 hertz band, it looks a bit different, narrower, and also still shows interesting features here. Okay, ideas for further studies are the systematic comparison of measured microbaroms amplitude with data on occurrence of rough seas or real model predicted microbarom amplitudes for my observation site. Unfortunately, both seems difficult to find in archives. I was not successful so far to find an easily accessible archive on sea state. And the other project would be to build a stereo device for also resolving the azimuthal direction of the signal, to find out whether the signal is coming from North Atlantic or from the North Sea, or perhaps even sometimes from the Mediterranean Sea. This would require a pair of sensors in a couple of meters distance, which are then read using the same data logger unit. So 2 channels for one sensor and the other 2 channels of the 4-channel device for the other sensor. Finally, I would like to point out 2 nice videos in the context of microbaroms. One is a video showing the global distribution of microbaroms, exactly the thing I would look for in a digital manner for my observation period. This has been provided by Milton Garces. And the other YouTube video details on the very surprising infrasound detecting capabilities of pigeons and other birds who are also taking advantage of the natural infrasound background in this frequency range for their navigation. That's all. Thank you so much for your attention.